And welcome back to track one on the first ever, and possibly last, based on the way I'm feeling at the moment, Software Circus virtual event. I'm here with Matt Jarvis from Day2IQ. How you doing, Matt?
Good, good. Hello, Mark.
My compliments on your outfit.
Thank you. My cape.
I feel like there's been a...
This is my normal clothes, by the way.
Sorry, it's just Thursday for you. Nice. I'm going to give a quick shout out to the sponsors who've made all of this possible. That's Packet, where I work, Container Solutions, Rancher, OfferZen, the CNCF, Honeycomb, Aqua Security, Kinfolk, Giant Swarm, and CloudBees. Matt's going to be talking to us today about operators, it appears. I'm seeing the word operate a lot in the title. So the only thing that's left for me to do is give you my canned applause to welcome you to the stage. Take it away, Matt.
Thank you very much. So this is me. I'm Matt Jarvis. I'm Director of Community at Day2IQ. Day2IQ are a software company working in cluster orchestration based in San Francisco. So today I'm going to be talking about operators, which I'm sure most folks will know by now is the new pattern for how we run complex apps on Kubernetes. And by complex, we generally mean stateful distributed applications. So this is a kind of application which is clustered or coordinated together in some way and has state or data retained across its life cycle. So generally, these apps have specific ways they need to be managed in order to operate correctly. And this is domain-specific knowledge, so it's unique to that application. So that set of tasks for a Kafka cluster is different from that set of tasks for a Cassandra cluster. So operators essentially bundle up that domain-specific knowledge that a human application engineer would have and allow you to orchestrate those actions using native Kubernetes APIs, typically by using a custom controller inside your cluster and a set of custom resource definitions. So there are a lot of ways to build operators. Originally, the Operator SDK from CoreOS. But today I'm going to be talking about KUDO. And KUDO is a polymorphic operator, which means it has a single controller for all instances. And through configuring it, it can basically become an operator for all different applications. So in comparison to other methods of creating operators, KUDO also doesn't really require you to write any code. Its configurations all just YAML files, which are orchestrated using a set of built-in Kubernetes objects, which allow you to sequence the execution of sets of actions. So the idea is that you can ship the runbook for your application together with the application itself. Here's a high-level architecture diagram of KUDO. We have the KUDO controller installed in your Kubernetes cluster with a set of a default KUDO custom resource definitions. We have this operator CRD, which is the high-level abstraction of a particular KUDO operator. Then we have operator version, which is the CRD that actually contains all the things that KUDO needs to become an operator for a specific version of an application. And the purpose of that split is to be able to run multiple versions of a particular application using KUDO. And in this architecture diagram, you can see we've got two different versions of Kafka running under the top level Kafka operator. And then we have an instance, which is the actual instantiation of the application. And KUDO also has a CLI extension for kubectl. And we can install operators either from our local file system or from the upstream KUDO GitHub repository. And the core concept of KUDO is that it has these built-in ways to sequence tasks, which is this hierarchy that we're seeing on screen of phases, steps, and tasks. Steps have execution strategies, so they can be executed either serially or in parallel. And tasks refer ultimately to a YAML file or a set of YAML files which will be applied to your cluster when that task is executed by KUDO. And by doing this, you can build up pretty complex orchestration of your applications. And the idea is that you would do this just using the tooling you already have for managing your particular app. So rather than re-implementing something like MySQL dump in Go, you would just use MySQL dump and define some YAML to run that directly in your cluster. So as the operator space matures, one of the key problems is that our complex distributed applications almost never exist as standalone entities. They're usually part of much larger application stacks composed of multiple complex distributed apps. So it's a very common pattern to see things like Kafka and Cassandra all deployed together, with Kafka for messaging, Cassandra for longer term storage, and maybe other elements as well. Now, if we've got operators for each of these applications, we've now got a bit of a problem in how we coordinate all these things together. And to give you an example in the KUDO world, if we were to just try and deploy Kafka and Zookeeper together in a single YAML file using KUDO, we'll likely get lots of failures along the way as things come up at different times. If a Kafka cluster comes up before a Zookeeper cluster, then it's going to fail repeatedly until it gets a Zookeeper connection, for example. And that could be transient, but it might also cause a permanent failure. And the second problem we have is that there is no mechanism for communicating things between operators. So again, in the case of this example of Kafka and Zookeeper, if we scale our Zookeeper cluster, then there's no way of communicating that updated connection string to our Kafka cluster without changing the configuration for that as well and updating it. And one approach might be that we could write meta operators that operate all our other operators. And some folks are doing that. But there is already tooling out there which has mechanisms for both passing variables between objects and for tracking complex dependencies. HashiCorp's Terraform has been around for a very long time in the cloud world and is a framework for defining infrastructure as code. So it allows you to declaratively define what you want to exist, and Terraform will work it out for you. Actioning changes using various providers which talk to your infrastructure layer. Typically, it's used for building cloud infrastructure for virtual machines, load balancers, all that good stuff. But more recently, it's been leveraged for defining application infrastructure in things like Kubernetes. And what makes Terraform pretty powerful is that it maintains these dependency graphs all the time, which allow it to make decisions on what things need to happen in which order, even if it doesn't know at that point exactly what the outputs will be. And by that, I mean that it knows something will change in a certain component, but doesn't know what that value will be until it's executed that and it stores those changes in its graph. Terraform also has a pretty powerful set of abstractions for being able to pass variables between objects in its graph, allowing you to build up variables from the outputs of other resources, for example. So one of the core KUDO team, Tom Runyon, wrote a proof of concept Terraform provider for KUDO, which lets Terraform control KUDO and defines a set of Terraform resources for operators and instances. And using this, we can actually deploy KUDO operators to Kubernetes clusters in Terraform as an entire plan. So we can rely on the Terraform dependency graphing and its ability to pass variables between objects in order to solve some of that dependency chaining problem. So the code for this provider can be found in the KUDO Builder repository on GitHub. And let's take a look at how this might work in action. So here's an architecture diagram of what we're going to build in this demo. We have a Zookeeper cluster and a set of our microservice apps, which are connected to Zookeeper using a connection string to configure them. And then on the other side, just so we can visualize what's going on, we're going to serve up the same connection strings we're using on an HTTP port through a load balancer to another simple microservice, this watcher, which is going to write that out to its logs. And when we run the demo, we'll connect to those logs to see what our apps are using for their connection string. Okay, right. At this point, I need to switch my sharing. Just bear with me 1 second. Let's go over here. And hopefully this is now the full screen, my terminal. So before we actually run this demo, let's take a look at the code. On disk here, we have the KUDO operator for our microservice. KUDO can install operators either from the local file system or from the upstream GitHub repository. So for this one, we're going to use a local checkout. And all KUDO operators have this standard file system layout. At the top level, we have this operator.yaml. And in our operator.yaml, this contains all the plans and their tasks for this particular operator knows about. So we can see that for this operator, it has a deploy plan. And the deploy plan has these steps, deployment and service. And for each step, we have these tasks, update deployment and update service. And we can see it also has this plan called Canary. And this has 3 phases, each with their corresponding steps and tasks. And when we look down at our tasks, we can see what will actually be executed when these tasks run. So these are the YAML files which will actually get deployed into our cluster. And some of these tasks are apply tasks, and some of them are delete tasks. And then we have this params.yaml file, and this contains all the parameters which can be set for this operator, which image file to use, which port it'll use, how many replicas. And for the purposes of this demo, we're particularly interested in these 2 parameters here, prefix and postfix. These are what we'll use to mock up how we can change our Zookeeper connection string. And we'll see more of that when we look at our Terraform config. Then we have this templates directory, and these are the actual YAML files referred to in the plan. And so we can see this is a deployment for Kubernetes. And KUDO, you can see this is templated, and KUDO will interpolate these parameters for when this is instantiated. And we can see that our 2 variables there, prefix and postfix, are being put into this end var inside our container, which is called header. And those are what will be served up by our web server on our back end. And we can look at our Canary deployment file. This is pretty similar to our original file, with the exception of some changes to the name. Very similar configuration. And we also have services for both the deployment and the Canary, which are creating a load balancer. And then for our Canary plan, we also have this verify Canary step. The Canary plan is basically a fairly typical Canary deployment, where we're going to create a single instance with a changed configuration, check it works, and then change our main deployment. And our verify step here is actually just mocked up. This is just a 40-second sleep. So let's go ahead and look at the Terraform configuration we're going to use to build this demo. So in our Terraform config here, we have a set of configuration related to the KUDO provider, where it can find our kubeconfig file, which version of KUDO it's going to install. Then we have this KUDO operator resource for our Zookeeper operator. So this is going to install the upstream Zookeeper KUDO operator from the GitHub repository. And we're going to not actually instantiate it here within this resource type, because we're going to define a specific resource type just below here. And we're going to initially deploy this with 3 nodes of Zookeeper. And then we have some of the Terraform magic, that we have a variable here that's being created from the output of the resource, the KUDO instance resource that we just looked at. Then we have our KUDO operator for our microservice, and then the KUDO instance for our microservice. And here we can see that our postfix parameter is being populated by that Terraform generated variable above. So we've both got dependency, and we're able to fill this variable with information that's come out of a previous step in the Terraform dependency graph. And then finally, we're going to deploy our watcher pod, and this is going to connect to our load balancer on the ports that we saw in the parameters file. So let's go ahead and actually run this. And what we're going to do here is just watch what's going on in our cluster. Just check this all looks correct. So now we can see things starting to happen in our cluster, and we can see that that Terraform has initially started our watcher pod, because that doesn't have any dependencies on anything. But then it's also deployed the KUDO operators into our cluster. And what we should be able to do with is do kubectl get operators and see both of those operators installed now. And it hasn't started yet. It's just starting to create the instance of our Zookeeper operators, so the actual Zookeeper cluster. And we'll start to see the 3 nodes for that appear. And the KUDO CLI extension gives us methods by which we can check what's actually going on with the particular plan that's being executed. So we can do kubectl KUDO plan status -- instance zook. And this shows us that the deploy plan is in progress and the deploy step is in progress. And once the deploy step is completed, the remaining steps are going to be this validation and cleanup. So what we're going to see is a validation step, a container spinning up in our Kubernetes cluster that's checking that that Zookeeper cluster is fully operational. And what's important to note here is that the deployment here is being handled by KUDO via the KUDO provider. Terraform is just providing the top level, the top level orchestration on how the ordering of things is going to be applied. So any second we should see our validation step start, and there we go. There's the validation container creating. And this is just checking that the Zookeeper cluster is fully functional before it actually starts our application. And again, we'll see the plans having changed in our KUDO output status. So we can see that entire plan for the Zookeeper operator is now complete. And so Terraform has received that status from the KUDO provider and has moved on to creating the instances of our running app. And we can also use the KUDO CLI extension to look at the status of that particular plan. And for our info app, we're seeing that the deploy plan is in progress and the deployment step is in progress. And the final step will be the service that we saw in our service.yaml template. And that should now be completed. So KUDO's executed that plan, and our demo architecture should have been deployed correctly. And what we can look now, if we do kubectl logs watcher -- follow, and what we're now seeing here is from the load balancer on the back end is our Zookeeper connection string from each of our application instances being served up, and the watcher is picking them up off the back end. And you can see those are all the same, and they refer to the 3 existing instances in our Zookeeper cluster. Now, at this point, if we were to scale our Zookeeper cluster just using KUDO, which we could do by doing something like kubectl KUDO update -- instance zook -p for parameter change, node count equals 5, then KUDO would go ahead and upgrade and scale out our Zookeeper cluster. But there's no mechanism for us to pass information between those operators. So there's no way for our application to know that that has changed without us updating our application config. So instead, we're going to do that in Terraform. And we're going to change our node count here for the KUDO instance of our Zookeeper operator. And so what we're going to expect to see is that when we change that in Terraform, Terraform will then pass that down via the KUDO provider down into KUDO. And then once KUDO has scaled that deployment to 5 nodes, Zookeeper Terraform will update this variable, the ZK connection variable. And at that point, it's going to pass that variable down into our KUDO instance app. And if we look at in our params file in our microservice operator, what we see is that a change in that variable will trigger the canary plan. And so it will step through all of the steps, phases, and tasks that were defined for this canary plan. Once it sees that variable has changed. So let's go ahead and change that variable. So we can see that for our KUDO instance of our Zookeeper operator, we're going to change that node count from 3 to 5. And also for our KUDO instance of our app, Terraform at this stage knows that there will be a change, but it doesn't know what that change will be until after the Zookeeper cluster has actually come up. So now what we're going to see is KUDO scaling out our Zookeeper cluster. And again, operators are really all about encapsulating that knowledge about how to safely do these kind of operational tasks to these distributed applications. So the KUDO operator for Zookeeper knows exactly what it needs to do in terms of scaling the Zookeeper cluster. So first of all, it's going to bring up the 2 new nodes. And then it's going to restart all the existing nodes in the cluster so that all of the 5 nodes at the end will have the same connection string. So while that's happening, we can actually see there already we've got our 2 new nodes starting to deploy there. Let's have a quick look what we expect to happen when our canary plan, once our Zookeeper cluster is up and running again, and that variable is changed by Terraform. So we're going to see a canary deployment, which will put a single instance of our app with that changed configuration with its own service, so that our watcher on the back end can see what that changed connection string looks like. Then we're going to run the verify canary process, our mocked verifier. In the real world, clearly that would be something that's going to check function. But once that step is completed successfully, we're then going to update the deployment and the service of our original set of applications. And once those are all up and running, we then clean up our canary and clean up our verification stage. So we can see now that our original Zookeeper instances are now starting to terminate. And we can take a look and see what the status is of this plan again. Using the KUDO CLI, we can see again we're executing a deploy plan for our Zookeeper operator, and the first stage of deploy is in progress. And there goes our second instance of our original Zookeeper cluster restarting. And what we'll expect to see, again, the deploy plan is executing, so we're going to expect to see our validation step to check correct operation of that Zookeeper cluster once the KUDO operator has successfully scaled and configured all 5 nodes of that new sized cluster. And obviously at this point, our backend application is still completely unaware of that change. So it's still really referring to only to those 3 Zookeeper nodes that were in our original config. And our final Zookeeper node is now terminating, and we'll restart. Once this final node recreates, we should then see our validation plan happen, at which point Terraform will see that this plan is complete and move on to running the canary plan for our info app. So all our nodes have now restarted. So what we would expect to see in our plan is that at some point very soon, our deploy step is going to complete. And any second, we're going to see our validation step start to happen. And there's our validation step from our plan happening right now. So this will show that all of our steps have been completed. And at this point, Terraform now realizes that it can move on, and it's triggered the change to that variable, which has then triggered our canary process. So we should see, if we look at our app, we can see that our canary plan has been triggered. And if we now look on the back end, what we should see is that there is an updated connection string in here, which is coming from our single canary instance. So the canary instance has that full connection string required for that 5-node Zookeeper cluster. And the canary verify process has now started. And once this has run for 40 seconds, then that will terminate, and all of our running nodes will be upgraded to that new connection string. So if we look at our plan again.
Matt, just a quick update. We have approximately 2 minutes left.
That's great. I'll be on time, Mark. Thank you. So we can see here that our verify canary is in progress, and that's now completed. So what we're going to start to see is our original application nodes all start to restart with our updated Zookeeper connection string, and we'll see that in the back end that these will all now change to being as those come up and running, they will all change to the new 5-node configuration. So we've seen that happening here. See, all our nodes have now changed. And any second now, that plan will have completed. Okay. And we should see that completes, and that Terraform now sees that plan is completed, and our configuration has been updated across all of our backend microservices. So let's stop sharing that for a second and go back to this one. This one. There we go. Right. Well, hopefully that demo has shown how this combination of KUDO and Terraform can act as the glue between multiple operators within a Kubernetes cluster to handle that variable passing between those operators. This is only one way of achieving this kind of result. In the future, I think what we'd really like to see is standards emerge in the operator space for handling dependencies and mechanisms for advertising available services between operators across the ecosystem, so that we can have more interoperability between operators, no matter how they were built. If any of this has been interesting, you can find out lots more information about KUDO on our website at kudo.dev. All the code is in GitHub under the KUDO Builder GitHub org. Development all takes place in #KUDO on the Kubernetes Slack. There is also a mailing list and a bi-weekly community meeting. You can pick all that stuff up off the website.
Matt, thank you so much. Let me get the canned applause in here. There we go. That's
fantastic.
You've gone for what I call the Holy Trinity, which is a relatively complex demo during a short talk that started late during a global pandemic. Bravo, sir. That hits all the points.
I like to go big, Mark. I like to go big.
You like to go big. The slides will be shared later. If you want to reach out to Matt, you can find him on Twitter or through the Brella app. We're going to have to end now because I have to get over to the next lightning talk. But Matt, once again, thank you so much, and especially for coming.
Sir.
It's what you normally wear on a Thursday, but I mean, what are the chances?
Yeah, let's hope we can see each other again in person for a beer very soon.
I would like nothing more. Okay. Bye-bye.
Bye.